Hello and welcome to the video. Today we'll be looking at gears and the kinematics behind them. So as an example, we're going to be using the gears on a bike. This is a little children's bike that I had lying around. And as you can see, the driving gear, so the gear that you spin with your feet, has a radius of about 7 centimeters. Meanwhile, the driven gear, or the gear that spins the wheel, has a radius of about 3.5 centimeters. So about half of the driving gear. So now let's go into tracker and let's look at the motion of the bike gears. So here's tracker, and as always, I'm just going to let the motion play. And as you can see, the driving wheel just makes one rotation. Meanwhile, the driven gear makes about 2 rotations in the same space of time. And as you saw before, the radius of the driven gear is about half that of the driving gear. And this should give you a clue as to how we can find the ratio between the angular velocity of the velocities of the two gears. Now let's go and do just that. Here I drew a sketch of the situation we just looked at. You can see we have gear 1, or the driving gear, which has a radius 1, and the driven gear, which has a radius 2, and they have their corresponding angular velocities omega-1 and omega-2. Now notice that since they're connected by the chain, their velocity on the outside of the radius, or where the chain meshes with the gear, must be equal, since the chain can only move at one velocity. If it wasn't, it would be violating the laws of physics and all sorts of things would happen. So as such, we can conclude that the velocity is equal to omega-1 times radius 1, since the angular velocity times the radius gives us the velocity on the outside of the wheel, or in this case the gear, which also equals omega-2 times radius 2. So from that we can get that omega-1 r1 is equal to omega-2 r2, and that omega-2 is equal to r1 over r2 times omega-1. So in the case that we just looked at, since r1 is twice that of r2, omega-2 is about twice that of omega-1, which is what we saw in tracker. And just to drive the point home, here's the graph of what we just looked at in tracker. You can see the driving gear this is the angle of the gear relative to the vertical, but you can see that the horizontal, but you can see that the driving gear has a much lower slope than the driven gear. And as you know, the derivative of the angle is the angular velocity. And you can see in the fit lines that the driving gear has about half the slope of the driven gear. Now, I didn't have an example to show for the next case, but it's very similar to what we just looked at. There's just one key difference. The example is when the gears, instead of meshing through a gear, mesh with themselves, so the teeth themselves mesh and spin that way. The one key difference is that now there is no chain or belt to connect the gears, but there is still a velocity which connects them where the two gears are meshing. And once again, that velocity has to be the exact same for both gears. And since there is no chain and they're meshing with each other, they will spin in opposite directions. And that should be you can try it with your fingers and you will see why that is. But we get that velocity is equal to omega 1 r1, which is equal to negative omega 2 r2. It's the same thing, just with a negative here. And once again, omega 1 r1 is equal to negative omega 2 r2. And so omega 2 is equal to negative r1 over r2 times omega 1. So if we had the same gears and instead of a chain, mesh them with their teeth, we would see that omega 2 would be would have twice the angular velocity of omega 1 and would be spinning in the opposite direction. And that is everything. Hopefully this helped you understand gears a little bit better, and have a great day. Goodbye.